since you mentioned Kuhn, I'm curious. Like, so I haven't really heard you discuss Thomas Kuhn much and his whole notion of paradigm shifts and stuff. And I was recently just writing an essay on Kuhn for my master's degree, and he has this like infamous chapter X where he says,
Yes,
when the paradigm shifts, it's as if reality itself shifts. So here's very
yes.
content. I probably can't imagine what I probably know what you're gonna say about this, but just in general, I mean, yeah, the two big philosophers of science that are discussed, they're almost like I'd say Thomas Kuhn is almost like a bit of a mini celebrity in philosophy of science.
Mhm.
What are your views on, Thomas Kuhn, his notion of paradigm shifts, and then the other big one, if I may also just add as like an addendum to that question, would be Kuhn-Popper and falsification. These two big figures. Just
Yeah.
generally, Professor, what are your views on them?
So, look, Kuhn is a mixed bag. And as you say, there's the X-rated chapter X in the Structured Scientific Revolutions,
Yeah.
and pretty much 1 through 8, I like those. I mean, Kuhn brought serious historical understanding of science to the discussion of science. And at the time that happened, that was new, and you had a lot of kind of cartoony science. People really hadn't studied the history, they didn't understand it. They had very cartoony views of it. And the serious historical study of science was a really, really good thing. And Kuhn gets a lot of credit for that. Um, the stuff about you have to be careful. He defines incommensurability between paradigms. He actually does define it, and i- paradigms are supposed to be incommensurable if the things postulated in one cannot be defined in the vocabulary of the other. That's essentially
Of the
the
other,
idea.
yeah.
Yeah, and okay, you can say that. The problem is what people think is that incommensurability in that sense means incomparability, that if they're incommensurable, you can't say one is better than the other, or one is better supported by the evidence than the other, or one is more credible than the other. That's just completely false, right? So in Kuhn's sense, I mean, Aristotle had a theory of matter, right? There's earth, air, fire, water, and ether. That's what there is. That's incommensurable in Kuhn's sense with modern chemistry. Because if you ask, but in terms of modern chemistry, what is Aristotelian ether? The answer is you can't define it in terms of modern chemistry, right? Um, but if you were to say, but doesn't that mean we can't say that one is better than the other? You say, of course we can, right? I mean, Aristotle was wrong, right? I mean, Aristotle thought the moon was made out of something very different than the earth. And, we've been there, we brought rocks back, and it's not. I mean, there's this slide between incommensurability, as Kuhn defines it, and incomparability. And people think incommensurability means incomparability, that you can't rationally say one is better supported by the evidence than the other. And that's just nonsense. Unfortunately, Kuhn himself says things like that sometimes. And, I mean, you have to remember, I mean, I don't know if you know the history here. Originally, Structure of Scientific Revolutions was supposed to be part of the Encyclopedia of Unified Science, which was a
I didn't
bunch
know
of
that.
little books, right? A whole bunch of little books. And so it was very limited in how long it could be. And they actually wanted somebody else to write it. I can't remember who. And the other person said no, but there's this young kid, Kuhn, asked him to do it. So they contracted Kuhn to write this thing, and he did. But he always thought of that as a first draft of what should have been a much longer and more careful discussion. And he kind of, for the rest of his life, tried to produce that and never did. And I think the reason he never did is he couldn't even make sense out of what he said. I mean, he just couldn't get this idea of incomparable, this kind of weird idea that science is not getting closer to the actual way the world is. And so he couldn't really make sense of it in the end. And I think that's why he never really published the big book that he thought he would publish. Um, but I don't want to take that much away from, I mean, I don't want to take away, he did serious historical work. His book on black body radiation is nice. I think the Copernican Revolution book is very nice. And I think the first 8 chapters of of the structure of scientific revolutions is very nice. I just think it goes astray at the end. Now, as for Popper, I guess I would say Popper, again, if you read him carefully, he's more subtle. There's a cartoon Popper that people often appeal to, um, about falsifiability as if it's this absolute thing. If you read the logic of scientific discovery carefully, he's pretty careful and he puts in the right caveats. I would say I like Lakatosh better. You know, Lakatosh was Popper's student, and he thought he was producing a better, more refined, more defensible version of Popperianism, and I think he did. Um, so I myself think that the insights you can get out of Popper, such as they are better accessed through Lakatosh. That's just my opinion there. Um, I mean, Popper's in a way easier to teach to undergraduates,
Was Lakatosh? I
although
haven't read much of Lakatosh at all. Like, is he the one with the research programs notion and all of that?
yeah,
Like invented the concept?
yeah,
Yeah, correct.
research
Yeah.
programs. I mean,
I mean,
the
we.
methodology of scientific research programs. I mean, his the book based on his thesis, Proofs and Refutations, is about the methodology of informal mathematics. It's just wonderful. It's written as a dialogue of this teacher and their students, and it's lively and funny and really deep, really deep. I mean, I think
Mm.
Lakatos is terrific. He unfortunately died in a car accident rather young. Um,
Okay, yeah, yeah. I mean, obviously, the I guess the big prize in the philosophy of science is given. It's after the Lakatosh Award or the Lakatosh Prize, right? So it's like
Mhm.
I really should read more of him. I know of him because of just like the other Popper and the rest of the philosophers of science. But I think if you're saying he's worth reading more than even Popper, I'll definitely give him my
Look, I
time.
mean, again, Proofs and Refutations is a funny book because it's not about empirical science, it's about math, but it is just a
Mathematics.
delight. It is a
Mm.
delightful book. I mean, if you just read it for fun, and it's deep. I mean, it's just lovely. Um,
Yeah, yeah. So, all right, Professor, when you were talking about this whole notion of incommensurability and kind of paradigms and whatnot, one from this is the book, Quantum Non-Locality and Relativity. And then in the first chapter itself, in this, where you were outlining Bell's theorem, so you kind of, you say, okay, what is weird about the quantum connection? And then you outline, well, you enumerate 3 points. The quantum connection is unattenuated. The quantum connection is discriminating, and then the third one you say the quantum connection is faster than light, instantaneous. So the
mhm.
entanglement bit, and then afterwards you keep going, and then the latter part. I'm just going to read out this bit just for more for the listener. You say. Our concern will almost be with the last of these three features. So the instantaneous spin, and you say it is surprising that the communication between particles is unattenuated and discriminating, but often our best counsel is simply to accept the surprising things our theories tell us. Then you keep going. The speed of the communication is another matter. We cannot simply accept the pronouncements of our best theories, no matter how strange if those pronouncements contradict each other. The two foundation stones of modern physics, relativity and quantum theory, appear to be telling quite different things about the world. To understand and perhaps resolve that conflict, we must consider carefully just what relativity tells us about space and time. So the reason I read that bit out was, you know, if let's call it like a quasi Kuhnian, or like like a caricature of Kuhn would say, oh, does this mean quantum theory is a paradigm shift in science, and suddenly we have to move from relativity to kind of the world of quantum mechanics. So to that kind of argument, and I know I don't think Kuhn would say this
Mhm.
either, but how? So just yeah, I know there's a lot here, but like if you could just outline this incommensurability, but also why we should not view something like quantum mechanics as like a paradigm shift and gives us like a new reality or whatever, as bizarre as that sounds.
Well, I mean, in Kuhn's terms, of course, quantum theory is a paradigm shift. I mean, no one would dispute that. But
Mm.
a paradigm shift from what? From Newtonian mechanics. from
Okay,
Boltzmann
okay, yeah, true.
and from Maxwell. That is, quantum mechanics is in the first place essentially a theory of matter. It is not a theory of space and time. It tends to just take some given space-time structure as given. And in terms of that space-time structure, and so that's why you've quantum mechanics that you first learn is set in classical space-time, in the space-time of Newton, essentially. Um, and then there's a question, well, can we do this in relativistic space-time? But so the subject matter is what is the nature of matter and how does matter work? Quantum mechanics is certainly a paradigm shift from Newton, from classical mechanics and from classical electromagnetic theory, Maxwell, for sure. Nobody's going to dispute that. And the reason we take it seriously is that it just makes that classical physics, classical theory of matter ran into some problems it couldn't solve, like the stability of matter. It just couldn't, if you take essentially Maxwellian electrodynamic theory and try and understand atoms, you're going to say that electrons are going to spiral down into the nucleus and, the whole thing's going to fall apart. So there was a question. And quantum mechanics certainly makes better predictions in that regard, right? It
Correct.
doesn't predict that matter will destroy itself. So that we have every reason to think that in some way, quantum mechanics is closer to the correct theory than Newton's theory, and that is a paradigm shift. But it wasn't about space and time. What I'm pointing out in that statement, and I actually forgot I wrote that, but I'm giving talks literally now called the I don't know, the Great Tension, which I'm making exactly the same point 40 years later. The point I'm making there is that it's a very different thing to say that quantum mechanics, which we have very, very, very good reason to take seriously, and relativity, which we also in some sense have very, very good reason to take seriously, contradict each other, right? You
Yeah,
can't take them both seriously. I mean, that's not a matter of incommensurability. That's a matter of logical incompatibility, right? They just, I mean, if one
it's
says
an
nothing goes faster than light and the other says something goes faster than light,
yeah,
I can't wrap my head around that and say, well, I'll just accept both of them, right? Something's got to
that'd be
give.
absurd. Yeah, that'd be absurd. Yeah,
And my view is that what has to give is relativity, that the relativistic account of space-time structure isn't right. That's actually this big book I've been working on, and other people, if you say relativity isn't right, then of course you're obligated to say, well, what do you replace it with? I mean, and that takes work, and there are different possibilities, and you have to try and think them through, and you have to try to articulate them and actually do some theorizing in terms of them and so on. It's hard work. But this isn't incommensurability. This is logical incompatibility. That's a problem that no paradigm shift can make go away, right?
yeah, yeah. That makes sense. I mean, so I guess the argument you're trying to develop is we need to pick one side, so to speak, in the
Yeah,
sense that we
and
gotta
furthermore, I think
Janice and
we know
relativity,
which side it has to be, because
and
the thing that indicates that there's superluminal causation is violations of Bell's inequality.
inequality.
And you
Yeah,
just see that in the lab. You just go into the lab, you do some experiments, you collect some data, and you say, hey, this data violates Bell's inequality, right? And as soon as you have that, you say, well, no local theory can give me that. No
yeah,
causal local theory can make that prediction. So causal locality is out the window. And that means something does, as it were, at least there are causal connections that are superluminal. And if relativity is understood in a way as saying, which is the way Einstein understood it, that there can't be superluminal causal connections, then I'm sorry, you have to get rid of relativity. Then you should think, what should I replace it with? I think that's the
mm,
situation. I don't think it's like just, oh, I have two conflicting things. Which one do I give up? We have two conflicting things, and the experiments tell me which one to give up.